Great. So what I want to do is sort of quickly cover two things. I want to just welcome you to the Center for Computational Astrophysics, say a few words about what we're doing here, and then turn to W first and give you an update on where we are. So let me apologize for not being here Monday. I split my time between Princeton and New York, and I spend my Mondays at Princeton. The Flatiron Institute is funded by the Simons Foundation. Jim Simons is the Simons of Chern-Simons number. The combination of topology and starting the first quantitative hedge fund made him very wealthy, probably more from the hedge fund than the topology. He and his wife set up the Simons Foundation, which supports basic research in science, and about 4 years ago decided to set up an institute focused on computational science. And this is the institute, the Flatiron Institute. Its goals is to advance basic research with a focus on computation. We have a number of centers I'll talk about, but let me begin by talking about the Center for Computational Astrophysics. And broadly speaking, the people here fall into two groups: those who go from initial conditions forward, doing simulations, those who go from data backwards, using big data and computation. We have 6 research groups now. We'll soon grow to 7 on galaxy formation, an astronomical data group, compact objects, gravitational waves, cosmology and data science group, planet formation, and the dynamics group. The staff here consists, actually most people are here for the shorter intermediate term. We have 2 permanent senior staff, Rachel Somerville and Shirley Ho, and 7 junior researchers and sort of an assistant professor type positions are also meant to be long-term. But most of the nearly 60 people here are on intermediate or short timescales. We have 6 senior faculty who are cross-appointed with surrounding universities. Some of those were already at those universities, but many of them were recruited to the region for these joint positions and will return to tenured positions at those universities. We've done 4 junior hires with surrounding universities. We currently have a joint search going with UConn and anticipate doing a joint search with NYU next year. These positions are sort of half-time teaching for the first 3 to 6 years, and then become, assuming they get tenured faculty at the surrounding universities. We have a large sabbatical visitor program. For this coming year, we actually have 28 proposals for 4 slots, so it's going to be difficult to choose among the really superb people who were eager to come. We have a large cohort of postdocs, about 25 postdocs, and many short-term visitors. Lots of people here visiting on time scales from a day to a month. And one of the very nice things about being located here in New York is we're sort of on the crossroads on various length scales. It's very convenient to get here from the surrounding universities, from Stony Brook to Princeton to Yale, and of course NYU, Columbia, Cornell Tech, CUNY, the places right here in Manhattan. We're located right sort of in the center of Manhattan. And New York is also the cheapest place to fly into from much of the world, certainly from Europe. So we have many people coming through here, and encourage you. What we have been very fortunate to have lots of people do is they're going to visit Minnesota for a week and coming from Europe and come through here and visit for a day or 2. And so we've just got a terrific flow of people coming through. The Institute more broadly consists right now of 4 research centers. In addition to computational astrophysics, we have a Center for Computational Biology. We're actually searching right now for a new director, as the Leslie Greengard, who founded this center, has moved to run our Center for Computational Mathematics. We have a Center for Quantum Materials, and we're thinking about a Computational Neuroscience Center. And we're all located in this building. The zeroth order approximation, in a sense, is this is like a For people from Europe, this is 4 Max Planck societies, Max centers in one building. Though I hope we're less hierarchical than your typical Max Planck Institute. We have the auditorium on the second floor. We have the centers on the floors above from 3 to 10. Astrophysics is located on 5 and 6. There's lots of us up there, so come up and visit during a break. And then the 11th floor is our dining hall, and there's coffee. And I encourage you to come up to 11. And then we have a roof garden on 12. This may not be the nicest day to sun yourself on the roof garden, but it just opened. All right, so that's the Flatiron. Let me now turn to W first. W first, I think of it as resting on 4 scientific legs: dark energy, microlensing, coronography, and a general astrophysics program. And of course, folks here are familiar with the microlensing program. The instrument itself, there are really 2 core instruments. The wide field instrument, which is the workhorse for sort of 3/4 of the science. One can think of it simply as Hubble on steroids with 100 times the field of view and with 18 H4RG detectors. And then the coronagraph. Just want to quickly go through a few of the science slides. I assume people here are familiar with the microlensing program, but just touch on some of the other things that we'll do in exoplanet science. In coronography, it will represent a many order of magnitude improvement in contrast ratio on what we can do either from space or the current generation of ground-based telescopes, push us into the regime in which we will be doing direct imaging of gas giants. If we're really lucky, around the nearest stars, get down to rocky planets if things work well. It really is, I think, the key stepping stone towards HABEX and LUVOIR. This is what we will need to develop the technologies to get there. Another aspect of W first that I just want to advertise, because I think it's sort of the third path besides coronography and the microlensing to study exoplanets, is I think we have the potential to use this as a very effective mission for astrometry, and just want to give a sense of what a potential sort of advance it will be for beyond Gaia. Gaia has been really wonderful and revolutionary, but if we look at what we can achieve with W first, this is just from the High Latitude Survey. This is something we will get for free as part of that program. We anticipate that we can step out in distance and really explore the outer halo by using the Gaia data as a reference frame to push outwards. And I encourage you to look at this paper on AstroPH by Sanderson, Bellini et al. That looks at some of the things one can do with W first in astrometry. In addition to sort of the imaging mode and geo mode, I think there's a couple interesting ways to think about using it. This slide's from Adam Rees showing what one can do with Hubble for measuring parallax rather than looking at just a straight image. We can do drift the telescope. This spreads the starlight over many, many samples. With that, you have root and improvement. With a camera the size of W first, there's a potential to really push quite deeply. And I think one could think of doing a lot of the program we actually thought about doing originally with SIM for going after distant planets, either by using it in drift scan mode or looking at the spider diffraction pattern. Refer you to the paper by Peter Melchior et al., which I'm part of. Also, one can think about combining Gaia, W first, and radial velocities. And I think with that, that's an approach. Look, Tim Duncan's done some nice work recently with Gaia and radial velocities, and one extends that with W first. I think we can go after 10 to 100-year planets on 10 to the 100-year orbits. And that will sort of around the nearest stars. And that will be a nice complement, of course, to the microlensing program. Let me turn quickly to an update on where we are with politics. It's hard to get away from it in this world. The mission's in phase B. At a technical level, everything's going very well. The detectors have, we now have detectors that meet all requirements, that are mission ready. If you think about this, we've got the telescope in place, we have the detectors in place, we've really passed all of our key technological milestones for the camera. The mission is sort of moving along nicely. We have all our major partners in place, the contracts are out. Fortunately, during the shutdown, our contractors, including JPL, were still able to continue to work. Unfortunately, our Goddard colleagues were not able to, we lost over a month of work. In terms of budget, we had, the year started out poorly when the mission was given $0 and canceled in the president's budget. This was not good. But all major missions go through their moment like this. In our case, it was not because of any problem with the mission that we were experiencing. We've been recommended by many Academy panels. It was because JWST was delayed and overrun. And some people in OMB felt that astronomy needed to be punished for Northrop Grumman's errors. Fortunately, we have a lot of support for WFIRST in Congress. We have a lot of support on the decadal process, and the Senate restored the budget to close to the level we had hoped for. The House has passed a bill that brings it up to the Senate level. So there's a House-Senate agreement to come up to the level we want for 2019, basically. All we're waiting for is for the House and the Senate to, NASA is in that part of the federal budget that has not yet been passed. So the agreed upon number that the president will sign for WFIRST is set for at the level we'd like for 2019. There's this thing about a wall that people want to build. It has nothing to do with microlensing or WFIRST. Some of you may have noticed something about it in the news that has stopped us from getting a federal budget. But when we do get a federal budget, we anticipate it will be at the level to keep us on track. What I don't know the answer to yet is what will be the impact on the schedule. Will we lose effectively a month or even perhaps 2 because of the shutdown with resultant costs? And our colleagues at NASA have just gone back to work. I'm actually going to have a telecon with the WFIRST leadership tomorrow morning to go over what this will mean for budget and schedule, but we'll need to figure that out. I am hopeful that the impact will not be too large.
You said things are proceeding well with the camera, but does that mean also coronagraph? Or?
Yeah, the coronagraph's moving on as well. So there's the coronagraph. I would say the biggest challenge with the coronagraph has been that in order to stay within the 3.2 budget cap that we've been given, there have been some descopes on the coronagraph. So that the coronagraph is technically ready. We're, I think, taking higher, the coronagraph is a technology demonstrator, which translates to we are taking, I think, more technical risk with the coronagraph than I think many of us would prefer. I think many of us would like there to be more funding for the coronagraph, but I think it's going to be very capable and will advance the mission. None of this here has been decided, but just where we're thinking, just remind you that the current science team is the Formulation Science Working Group, And the FSWIG is, our job has been to set the requirements for the mission, and that the actual science team has not been completed or selected, right? So we're still looking at, we'll have a competition for that. We may have multiple rounds of competitions where we may compete on the initial science teams in the next several years, and then after launch have a second competition which will involve the second half of the baseline mission, and then future competitions while the mission is designed for 5 years. We all anticipate and hope it will operate for at least 10. And one of the challenges I want to give to folks here, when you look at the mission, particularly since this is the microlensing program, is right now we have a design reference mission. It represents, for all of our programs, our current best thoughts on what to do. But science is advancing, and this is, I was, describing, this is really a different program operationally from Euclid or LSST, which really is designed so that there's a fixed program that the mission is built for. We have a lot of flexibility in how we use this powerful telescope. So one should think about the trade space of what science do we want to optimize for? What you read in the DRM may be the right thing to do, but if there are better ideas, this is what, write them up, or better yet, even propose them as we go forward. So I think it's an exciting mission for a wide range of science. I think for microlensing, this is one of the areas in which this is an enormous step forward. I think we can anticipate, I think of this as completing the exoplanet survey that we began with Kepler and now TESS in terms of characterizing the demographics of planets. I'm really pleased you're all here. And so both in my W1st hat and my CCA hat, welcome, and have a terrific meeting. Thank you.
Other questions for David?
Great. So, yes, Eric.
So I'll ask about the astrometry angle.
Mm-hmm.
What's the different versions of lifetime of W1st, and how many years after the beginning of Gaia observations?
Can you use your seat mic, please?
Push the button next to you.
On left or right?
Either one, right there. It's near the speaker.
So I was asking about microlensing. What's the W1st sort of baseline and most optimal mission durations? And how does that, I guess in its most optimistic scenario, line up with a Gaia astrometry start date?
So let's see. We're scheduled to launch in 25. And so our baseline is to operate for 5 years. That's after getting to L2. So I think depends exactly when we launch. Science operations, my guess will begin in early 26. So it's 26 to 31. And then we will certainly carry enough fuel that we will operate into 36. That's sort of what I think of what we'll actually achieve. The history of most missions has been, as you operate them, you learn how to be more efficient in fuel use. So, I don't know, 37, 38, 39, somewhere. That's post-retirement for me by easily, so I'm not so worried about the late 30s. But, but for astrometry, it'll be great. So you're looking at, with Gaia, an enormous baseline, right? So, I guess Gaia data began 5 years ago now. Is that right? Data release was 2.5. But so you're looking at a very nice lever arm. And the thing to think about is you have the Gaia. Every image has of order 1,000 high-quality Gaia stars in terms of the astrometry. Good. Great, thank you.
Thank David again. Okay, next we have Alessandro Sozzetti to tell us about Gaia Astrometry and exoplanets, and in crowded fields too.
Question mark. Hi, everybody can hear me okay? Yep, perfect, very good, yep. So good morning, everyone. Yes, it's Gaia time. It's been Gaia time since a long time, in fact. And it's now about 5 years into operations, 4.5 approximately, at L2. It has turned, in fact, more than 5 years old since launch in December 2018. Most of you know what Gaia is. It's a scanning satellite, and it's providing the highest precision astrometric measurements that have been delivered to date in space with a scanning pattern of the sky that covers the full observed celestial sphere down to the magnitude limit of the survey, 20.7, in approximately 6 months. And it does this every 6 months, covering entirely the sky. The biggest first spectacular contribution of the mission to the science community has been Gaia DR2. There was a first data release in 2016, but really the revolutionary impact in the field, in many fields of astrophysics, has come with the second data release. The second data release, as you see, has improved by order of magnitude the initial precision, approximately a small fraction of a milliarc second, provided by Gaia DR1 for a relatively limited interval of observed magnitudes by the survey. This is what Gaia DR2 has achieved in the astrometry department. We are still far from the end of mission forecast that should bring the bright star regime down to less than 10 microarc seconds in the measurement of the 5 fundamental astrometric parameters. This is the error on parallax as a proxy. There are some limitations coming with the Gaia DR2 that can be summarized through essentially a message based on we are limited by our knowledge of instrumental effects and a variety of systematics that still have to be dealt with. There is, at the faint end, an issue that we have to live with, not exactly deal with, which is additional stray light effects in the spacecraft that are actually producing a performance loss at the very faint end. This is something that we have to live with. Gaia 2 has been revolutionary. I will briefly touch upon a snippet of interest for the exoplanet community in a second. What's coming afterwards, however, is now in the plans. This is a very complex endeavor. We have been facing often delays, not because of lack of budget or funding, simply because it's complicated to interact in a consortium of several hundred people who have to really make sense of an extreme variety of data products that are all intrinsically connected and often correlated. The result of this complicated exercise is that often what was planned ended up slipping in time. The yearly data release plan initially set up before mission launch became something on a 2-year basis. DR1 was followed by DR2 after 2 years. And now things are maybe even going to get even worse. As of 5 minutes ago, I was going to tell you that DR3 was scheduled likely for the first half of 2021. I don't know if it's already up, but I have been given green light to tell you that there is an update on the data release scenario soon to come up on the Gaia website. DR3 is actually going to be staged in 2 steps. There will be an early data release 3 happening in the second half of 2020. This will bring only astrometry updates and extended object information, quasars and galaxies. The second step will actually happen sometime in the second half of 2021, and it will bring everything else, including the first information on non-single stars, meaning objects that are most likely binary in nature. So this is going to be what you have to read instead of this slide. As a consequence of this expanding timeline of data releases, the nominal 5-year end of mission data release is now entirely to be determined in terms of time, not only because of the additional time span of the preparations of previous ones, but also because of the fact that the extended mission is actually now a reality. Gaia had a 5-year plan plus fuel to run for an additional 5. And the initial extension approval has been now granted by ESA officially at the end of 2018 for 1.5 years. And there's another 1.5 year extending the mission all the way into 2022, likely to be granted sometime in 2019 by ESA. The plan is, however, to entirely double the mission lifetime. What have we done with DR2 science in the realm of exoplanets? Something, not much. DR2 provides, as far as astrometry is concerned, no information on binarity. You are getting positions, proper motions, and parallaxes. What can you do with those? Well, the parallax information has been folded to redetermine the stellar properties of planetary hosts, and thereby, especially for the sample of transiting systems, a revisitation of the physical properties, masses and radii of the orbiting companions. And then there is a class of approximately 3 different flavors of ways of treating varieties of implementation of a formula that describes a change in the proper motion between Gaia and Hipparchus. There are several ways you can do it, but ultimately you are calculating an effective difference in proper motion between Gaia and Hipparchus. And these have been implemented in a variety of clever ways, producing, for example, a category of accelerations combining Hipparchus and Gaia. And then, in order to put limits on the presence of stellar and stellar companions around nearby stars, and actually determine, in some cases, some lucky cases, actual dynamical mass estimates. I will go briefly through the second aspect. This is a case, for example, of a way of using the proper motion difference between Gaia and Hipparchus in order to place constraints on the presence of massive objects around the nearest stars, Proxima Centauri. And as you can see, as this is the nearest star to us, a very tiny difference in proper motion, even not very significant at the 2 sigma level or so, allows you to populate a family of potential, to exclude a family of potential companions down to very low mass giants at orbital separations of a few astronomical units. The more important exercises have been carried out by combining information that comes, for example, from direct imaging for objects that have been identified to be massive wide separation companions, radio velocity information, and again, information on the differences between positions and proper motions between Hipparchus and Gaia. And this is a case of a massive brown dwarf, HR 7672b, with its dynamical mass estimate coming from the constraints that are given by a chunk of radio velocity curve being covered, position angles and separation estimates from direct imaging, and then the differences in proper motion in right ascension and declination derived from Gaia and Hipparchus. And going down all the way to the planetary regime, this is as of today the cleverest way of using Gaia and Hipparchus data to detect the orbital motion induced by Beta Pictoris b, which is a massive planet of approximately close to the deuterium burning limit, 10 to 13 Jupiter masses, at the orbital period of between 25 and 30 years or so. And different groups have used either the full sequence of position measurements from Hipparchus in combination with the Gaia and Hipparchus proper motion information, or used the combination of, again, as I said, radar velocity information, proper motion difference information, and direct imaging positions of the directly imaged companion to actually constrain rather accurately to approximately on the order of 10–20% the mass of the companion. But this is as much as one can do with DR2. We don't have really information on binarity, and in order to detect planets with Gaia astrometry for real, with Gaia astrometry alone, you have to go through the exercise of making sense of deviations from stellar proper motion and parallax description of the stellar motion, and look for perturbations, higher order perturbations induced by an orbiting companion. These are typically orders of magnitude smaller than the value of proper motion and parallax that you end up measuring for a given target. And they often, when it comes to planetary masses, go down to a very small fraction of a milliarc second. Now, we have seen that on the order of 100 microseconds seems to be the floor for, especially at the bright end, that can be achieved by Gaia DR2. 100 microseconds is often a number that is already not very good in terms of positional precision in order to detect planetary companions. So we actually have to do better than this. How are we going to do it? Well, first, we'll have to make sure that the 5-parameter description in the general astrometric solution for Gaia is as robust as possible. And as I mentioned, there are still improvements that can be done, especially when it comes to the general calibration measurements of the instrument, model, attitude, and general geometry of the focal plane. This is something that is still going to evolve in a significant manner in order to meet the expectation of Gaia. If you have a good 5-parameter astrometric solution and you are rather confident that your excess residuals in the positions are not due to a modeled instrumental effects or systematics of variant nature, that means the star is not single. And then you have to go and see if you can describe its motion in the sky as seen by Gaia with a more complex model than a single star model. This is a task of the non-single star component of the Gaia data processing pipeline. It lives within coordination unit 4. And in principle, it actually is has been appointed a task of modeling binarity in all sorts of flavors. Gaia obtains also photometry and spectroscopy, and there will be also catalogs of eclipsing binaries, spectroscopic binaries, along with the astrometric binary component, as well as the identification of resolved binaries. Let's focus on the astrometry part for the purpose of this talk. This is the way non-single stars in the astrometry will be treated. It's going to be a cascade of different models, increasingly more complicated, essentially turned on if the goodness of fit of the previous, smaller, simpler model is not good enough, in fact. down to some statistics threshold that is going to be of choice. At the bottom of the line sits the modeling of astrometric orbits of planetary systems. This is the most complex way of describing orbital motion that we will be looking for, and it's going to be the one that is actually started the last. And as a matter of fact, it has not even started at all. The complexities in the identification of true binarity, so identifying a sample of stars that do not look single because they're actually orbited by companions and not because the data quality is still not sufficient, has been a very slow process. And as of today, we are still waiting to start actually the pipeline analysis of the expected hundreds of millions of stars that will come our way, identified not to be well behaved with a 5-parameter model. As a matter of fact, this is the reason why we have to wait DR3 for any reliable information on binarity to be produced by Gaia. The fundamental ingredient, as I mentioned before, that will have to be achieved with as high accuracy as possible, is anything as close as to the pre-launch predictions of the single measurement error. This is the number that is actually the one that matters, rather than the end of mission estimation of the accuracy on parallax. Is the per measurement uncertainty that matters for companion detection. And in the case of Gaia, at the bright end, you are expecting, this is the per CCD, approximately 40 to 50 microarc second, divided by the square root of 9, in the 15 to 20 microarc second regime. This is the best that Gaia is expected to do for bright stars. And this is where we're aiming, and this is where it's going to get very difficult to get. How we're going to do it with this scheme. Gaia, we look at stellar motion and companion orbital motion in the plane of the sky, rotated by the scanning angle, which will always be different given the scanning law prescription. And this is the modeling, especially in the along scan direction, which is actually the one that is where Gaia performs its most sensitive measurements, that we will end up looking for planetary and orbiting companions. This is the model. How is it implemented in practice? There are two flavors in the data processing pipeline. We have learned from radar velocities and other techniques in the history of exoplanet modeling that it's better to double-check your results, especially when it comes to complex models. And so there are two different algorithms implemented, one based on Markov chain Monte Carlo philosophy, and another one that uses an algorithm based on genetic algorithm approach. A snippet of how they are doing, not on real data, but on simulations, kindly provided by an internal simulation scheme within the Gaia consortium. This is a case of approximately 4,500 or so single planetary companions within a couple of hundred parsecs, orbiting bright stars with a planetary mass distribution, orbital period, and stellar mass distribution summarized here, which is not dissimilar from what you see in the literature, for example, for radar velocity work. And these are two brief snippets of the reconstruction of the quality of the orbital reconstruction using the two algorithms. For example, period is fitted pretty well by both, almost indistinguishably well as far as you constrain yourself to a time span of the observation comparable to the orbital period, so 4 to 5 years. In the long period regime, up to twice as much as the mission lifetime, slightly different systematics seem to appear in the analysis, with a little bit of overestimation or underestimation of the actual true period, depending on the two parameters. And this is a case instead of orbit fitting of the eccentricity. It appears that there may be biases in trying to fit the almost circular orbits. So there will be a typical overestimate of the orbit eccentricity for very low true eccentricities, while very high eccentricities, this is essentially due to primarily to orbit sampling, will be hard to get, and they will typically be slightly underestimated. Now, let's conclude with a view of what Gaia can do and connect it, especially as a matter of exercise, with some of the information that we've heard yesterday in the first day of the conference. The Gaia Discovery Space can be summarized in this slide. This is messy. It's similar to something that you may have seen in the past. It has one element of novelty, which is this. This is the expected regime of W1st microlensing survey covering the parameter space of planetary masses and orbital separations. And Gaia sits up here in two flavors, actually four. This is the limit of Gaia planet detection for, let's say, mid-M dwarf at 25 parsecs for the Sun. This is the limit out to the nearest star formation region, around 200 parsecs away in Taurus, for a solar-type object, for a solar-type primary, for a 5-year or a 10-year extended mission. What you come up with is the message that you will be able to access, using Gaia, or the order of millions of stars with sufficient sensitivity to detect planetary mass companions. And this folds into an expected reservoir of few tens up to several tens of newly detected planetary mass companions in the granted giant planet mass regime, around stars of all spectral types within the next couple hundred of parsecs from the Sun in the solar neighborhood. And so the fundamental contribution of Gaia to this field of astrophysics can be summarized in this line, with many orbital solutions of good quality, knowing the orbit architecture and the true mass of these companions. It will be possible to look for the fine structure of the orbital elements distributions, mass distributions of these companions as a function of stellar properties in a way that is not possible today. Even with the spectacular sample of thousands of Kepler targets, you're still limited to a regime of the parameter space that sits all the way up here for the time being. And this area will really be revolutionized by Gaia, in my opinion. A couple of synergy elements that can be seen in detail. Well, let's take a look at the recent result of the possible discrepancy between the observations of the mass distribution from Microlensing results and what we know from theory in terms of population of giant planets at intermediate separations or wider separations. We heard yesterday from Ruth Murray-Clay some of the questions she posed yesterday. I've caught up here. There are still things that should be learned, and the statistics that's coming from microlensing, in particular in connection to the variation of the mass distribution at wide separations, the actual contribution of lower mass companions, lower mass giants with respect to the high mass end of the distribution in this regime of separations, and the actual potential dependence of this distribution with orbital separation or primary mass are still to be understood. And in my opinion, this is one of the places in which Gaia will have a spectacular impact. It may not get down to mass ratios turn into true masses, thanks to the possibility of measuring with astrometry, of Neptune-type companions, but low mass giants down to sub-Saturn mass regimes will certainly be accessible. And the combination of Gaia alone information that would come from microlensing and the radio velocity service will be absolutely revolutionary in the years to come. On a similar note, if you look instead at the radio velocity work in combination with direct imaging that has been carried out so far, you look at, for example, tentative identifications of structure, for example, in the occurrence rate of additional companions in systems known to already host a giant planet at a different separation, whether it's very close in or a little bit more wider. Orbital semi-major axis. These initial inferences are relying upon a relatively coarse identification of the outer companions. If you look in particular at the analysis carried out in this paper, typically planetary masses are at the lower end of the allowed range of masses, and the orbital separations can vary by orders of magnitude. Because they rely upon essentially the identification of long-term trends in the radio velocity time series. Certainly, combined with direct imaging information, excluding some regimes of the parameter space of allowed companions is certainly good, but it's not enough to really characterize very accurately this element. And the possibility of detecting additional companions in Gaia astrometry, so multiple giant planet systems, is certainly there. It will be even more complicated than getting just one planet being identified. But if you do a simple exercise by combining these two works results, you can come up with a let's say, back on the envelope calculation that will tell you that there may be thousands of giant planet systems with 2 planets for the time being. That could be actually identified by Gaia, and for a significant fraction of these, it will be even possible to measure the relative inclination angle between the planetary orbits. And this will also come with accurate, up to some extent, eccentricity information. So the synergy is going to be spectacular, even in this case. This is as far as exoplanets are concerned at large, looking at any area of the sky as you want. In the last minute of the presentation, let me see if Gaia can do anything close to what we'd like to do in a generic field, in crowded fields. Before you get there, remember that you have to first solve this problem. And this will affect stars all over the sky. Bright stars are everywhere, especially out of very high density regions, but also in high density regions. And the possibility of really bringing down by an order of magnitude the unmodeled errors in Gaia astrometry, especially the bright star regime, is going to be the most difficult task that we are going to be dealing with in the next few years before Gaia DR3 comes up.
Is this single epic?
Yeah. Sorry. Yes, exactly. This is the same as I have shown in the simulation. This is again the expectation end of mission. This is what we're getting now, which is still coarse. In crowded fields, well, Gaia is going to do worse. As far as astrometric planet detection is concerned, don't expect much. That's my personal opinion. Galactic bulge, galactic plane, Magellanic clouds, they are very, very far. Stars are faint. Fields are crowded. Binaries may be possible to be identified, planets unlikely, with the setup that I've shown you before. furthermore, there are other complications that are coming, even for applications that, in fact, are in principle, however, possible. And here we are shifting to the modeling of astrometric microlensing events. They are going to be hunted for exactly in the most crowded regions in the sky observed by Gaia, although there are some predictions, we may hear more in a talk after mine, that in fact identify microlensing events in the astrometry at rather high galactic latitude. However, the bulk will come up here, and here you see from Gaia DR1 to Gaia DR2, there have been significant improvements in sense of, for example, of identification and population of the many missing objects that have been populated that have been not seen in DR1 with respect to DR2, but still, even DR2 in crowded region has trouble. And I'm summarizing here some of the most important limitations that one has to deal with. How to resolve or improve the performance? Well, this is an ongoing discussion. I can provide you a very small amount of information of ongoing work. There is an attempt at using what used to be an engineering tool. We call them science interface function images, SIF images, that were initially taken with a Gaia Sky Mapper at the beginning, the first CCDs in the focal plane, to produce the spectacular images that you have seen before, for example, this one. And not this, but others, for example, of the Omega Centauri area. The point here is to try to devise a scheme to use the SIF images to improve the astrometry and photometry, producing astrometric and photometric products that can actually be fed into the standard Gaia pipeline. This will be done specifically for the most crowded regions of the sky, Bardas window, globular clusters, galactic center, and also for some hundreds of the brighter stars in the sky. You've seen the behavior of the single measurement precision. It gets even worse when it gets to very bright stars. It's not just a floor. And the brightest stars, down to the brightest stars that we hope to be able to model, G-band 2 or 3, these are very, very few objects in the sky, and the standard modeling through the standard pipeline is impossible. There is simply, it's not possible to calibrate them with standard pipeline. So the SIF image use approach will try to deal with both. Right now, it's an open work area with very little done so far. I have been told to tell you that you should not expect anything before DR4. DR4 date is to be determined. So as of today, this is the generic plan that's in the works to improve Gaia performance in crowded regions, but there is right now no word on when it's going to be producing results, certainly not early. Thanks. I think I can stop here and take questions.
Questions? Let's start with David.
A scientific question about some of the tests that were shown early on, where you assumed a single planet around the star, and you saw it in your simulations if that could be recovered. Is that believed to be a reasonable assumption? So for the solar system, for example, if you assumed that it just had Jupiter, you should not recover or correct Jupiter because there's also Saturn, Uranus, and Neptune contributing astrometric noise.
Yeah. The single planet simulation results I've shown you is the first half, or a more complex simulation that we have been running to get the codes ready, and a multiple planet solution with not Saturn, Jupiter exact combinations, but similar with objects sometimes widely separated with period of just a few years and a companion up to 10, 15 years of orbital period. Those are part of the simulation that we are still looking into.
Two quick questions. One, you mentioned that it's going to be difficult to do the astrometry in the crowded fields, but we know from Gaia 16 AYE that there will be some events that are doable with Gaia. The astrometric microlensing signal of those events is extremely complicated, as is shown in that paper, which you're probably a co-author on. And with the images appearing and disappearing, I wonder if you have a filter that will allow you to find those things and not throw them out. And then the second question is if you can go back to your plot of the sensitivity. One back, one more. Yeah. One thing I've never understood about astrometric surveys is, and I think this is something that Andy pointed out a while ago and other people have pointed out as well, is that once you get to the limit of the duration of the survey, then the only way you can detect a companion is if it has curvature, which disappears quite rapidly when the duration becomes considerably longer, or even just a little bit longer than the period.
Yeah.
So it seems to me that those lines should be almost straight up, not curved like that. You see what I'm saying?
Yeah. Okay. So first, the microlensing. In the pipeline that deals with stars that do not look single or are affected by some physical phenomenon that is not model errors, astrometric microlensing doesn't appear. So there is no default recipe for the treatment of such, for the modeling of such signals in the standard pipeline. This doesn't mean that efforts may be made to ascertain the appearance of these, especially when they are predicted to occur during Gaia timeframe of these events. And there may be, now I'm actually wildly speculating because I really don't know what the plans will be. There may be an alert system that is set up in place for this. There's alert systems that have been working rather well for photometry to identify transients of a variety of types, particularly variable stars. Nothing has been done yet for astrometry, but that's potentially a possibility. As far as this is concerned, the curvature here tries to capture the continuous detection of a strong departure from linearity in the motion in the proper motion. The more massive the companion becomes. So you may say, let's stop up to maybe a little bit earlier than this, which is probably okay. But the general feature of the behavior of the detection curve, this turning point, the way it comes up, is actually well understood by keeping constant the amount of curvature that you see. The more massive the companion becomes, the longer the period, up to some point.
Okay, we have time for one quick question.
Coffee break later.
So I would urge you to make preliminary estimates of which stars have companions with possible 100% false positives. So factor of 2 error, in order that Sloan 5 could start monitoring these when they, at a higher rate. So they'll monitor all these Gaia stars anyway, but maybe with a few epochs, but the ones that are thought to have planets, they'll have more epochs. It'll really untangle things a lot faster. And the Gaia attitude that we have to, only send things that are perfect to the community, really nonsense and very stupid. So, you guys really have to change your orientation in a focused way.
I take the message home. I'll be happy to deliver it. There is always going to be a tension, however. The more complex the modeling and the more complex the larger the amount of data that comes out, the larger the danger of making important mistakes. And there will always be an attempt at making this as small as possible.
People who are not making mistakes are carrying out worthless work. So, you know, you should talk
I
to
know,
Hans
I know,
So-
I know,
so
I know,
let's-
I know, but
Let's take
I
this up to
entirely see on this
coffee.
point.
You've made your point, Andy. Thank you.
Ooh.
Okay, continuing on in the Gaia theme, next we have Katarzyna Krzyżynska talking about highlights from Gaia Microlensing Survey of the Galactic Plane.
Oh, there it is. Okay, so it'll count down from 12. Okay, thank you. So, hello everyone. My name is Katarzyna Krzyżynska. I'm a PhD student at University of Warsaw, and my advisor is Łukasz Wrzykowski. Today, I would like to present you some highlights from 2018 and years before that of microlensing events found in Gaia. So, as you heard probably before, it is very weird to maybe care about microlensing in Gaia because Gaia is not designed as a microlensing survey. However, in order to measure, well, microlensing allows us to observe objects which emit no light. And that means that we can maybe attempt to observe objects of stellar evolution, so the end products like single black holes, neutron stars, and white dwarfs. However, microlensing model is usually very difficult to analyze, and it is plagued with many degeneracies. And in order to directly measure the mass of microlensing the lens, we need both Einstein radius and Einstein parallax. However, Gaia is actually an astrometric mission, so it can help us measure the astrometry, right? But we still need good photometry in order to get the perfect mass measurement. So here are some things that I wanted to reiterate about Gaia. So Gaia is mainly an astrometric mission. It is located at the L2 point, which may become important in a second. Up to this day, there has been 2 public data releases, with GDR2 being a huge success in the Astronomical Society. And alongside, there has been Gaia Science alerts published every week since 2014, and on average, there are 4 transients published every day. The mission has almost finished its core mission. However, it has been already extended until the end of 2020, and further extensions are possible depending on the condition, mainly on the condition of the spacecraft. Here I have presented you the scanning law after 5 years of Gaia. And as you can see, though, the warmer colors mean that the field is observed more frequently, and the cooler ones denote the less frequently observed fields. So on average, Gaia observes a single star once every 30 days, which is already bad. However, the watchful regions will receive, after 5 years, around 40 to 60 points. So that's way too low for microlensing, and this is why we need follow-up. Here I have presented you a map with all the astronomical sites that we are observatories that we are using for follow-up. Usually we use mostly the telescopes which are in the Opticon network. We also apply for time in various smaller observatories, for example, Moletai in Lithuania or Vainu-Bapu Observatory in India. And in addition to that, we also apply for more professional ones with the great addition of LCO, where we managed to get a lot of time, and it provided beautiful light curves for us. In addition to that, we also get some help from the amateur astronomers, and this year it's very exciting because we managed to get some observations done with Spitzer. In addition to that, we also do spectroscopic follow-up of our events with the largest telescopes in the world. And why is that? I hope that I will convince you in a moment. So this is the map that I have. Yeah. Okay. This is the map that I have shown you last year. As you can see, there are around like 30 microlensing events. However, this has changed drastically this year because Gaia detection rates have improved. Can you hear me? Yeah, okay, great. The Gaia detection rate has improved due to the long baseline that it has gathered through last almost 5 years. The detection efficiency has improved in bulge, and that correlates with the 37 events that also occur both in Gaia and in Ogle early warning system. And in addition to that, we also have managed to get 17 spectra for 17 of our candidates. 5 events have been missed. 4 of them occurring here were in the Assassin survey, and here is the famous Kojima event. So we haven't been alerted on those. These are some highlights from the years prior to 2018. I want you to focus on Gaia 16 AYE because the paper is already on the archive, and I encourage you to read it. It's great. And we were very, very lucky to. So here is a beautiful model made by Przemek Mróz, and we are very lucky to be able to observe Earth-Gaia space parallax. So because Gaia was observing the event during one of the caustic crossings, which is very, very exciting. Additionally, there is Gaia 17 AQ with 3 spectra from SALT, Gaia 17 BTS with very noisy follow-up done with the optical network and 2 spectra from Palomar, and Gaia 17 CTL, which is a very high magnification event, which was caught in November. So that was very depressing. And here are some highlights from 2018. So first, I would like to present 2 targets that have been selected for the Spitzer follow-up. Gaia 18 BMT has both of them have spectra done on Spitzer, and here for Gaia 18 BMT we have wonderful follow-up done by here I only present SMARTS and LCO. With the red line, I have denoted the parallax model, the red dashed line, and as you can see, it is very, there's almost no signs for parallax. So this is why we need Spitzer. If we want to measure the mass, we need additional observations for, even though the events seem quite long, there is no information about the space parallax, parallax, annual parallax. So this is why we need Spitzer and space parallax in order to get our mass measurement. Here are some additional highlights for all of those sources. Those are one of the 17 sources that have spectroscopic follow-up done, with 2 latest ones done with SALT. I think the second one is hardly visible, but as you can see, there are beautiful absorptions lines visible, so yay. Here are 2 nice examples from objects which occur both in Ogle and in Gaia. As you can see, Gaia data is very patchy and Ogle data is very nice. And this is the slide that I would like to present you to show you that we actually need spectroscopic follow-up. So we are focusing mostly on very bright events with baseline brighter than 16 magnitudes in G Gaia band. And as for Y, I would like you to focus on Chris's talk, which will be after mine. But if we focus on bright events, it means that we expect a certain type of contaminant in this sample. And here is a little question. So maybe you know what that is. Okay, so here we have huge emission in H alpha, and I think that's a passion comb. It's a BE star. It's my favorite one. So if we want to send our target for Spitzer or for follow-up, we want to send them know about them as soon as possible. So here are some, like I would assume that that's a beautiful microlensing event. However, if we don't want to wait too long, we send our target for follow-up with spectroscopic. For spectroscopic follow-up, and if we wait a little bit longer, we will see that this event will have like this tiny step and then being completely flat, and that's an obvious BE star. Here are some other events from Gaia. As you can see, there is a wide variety of light curves with better or worse sampling, and here I would like to end my talk. With some future plans. So I encourage you again to read the paper about Gaia 16 AOE. It's a bitnet, and it's on archive. I am looking forward to the results of the Spitzer survey with Gaia. I am very excited about that. If you want to help us out with follow-up, you're always welcome. Just contact me. And I would like to also maybe hint for like the next year. We were been greenlit to do archival search in Gaia, which is very great, and I'm looking forward to the results. So thank you.
Questions?
Yeah, so I just wanted to point out that BE stars is masquerading as microlensing events are, you know, one of the main backgrounds found by Macho and Eros. And one of the two candidates by Eros, the first published ones, was a BE star.
Yeah, they are a very popular contaminant in my sample.
Can you say a bit more about how you alert follow-ups? In the US, you haven't. It looks like you don't have much coverage, and there's a lot of resources that could be employed.
Well, if I want to like read the question to understand if I got it right. So you want to know how we alert our events, right?
Yeah,
How do we look for them?
Oh, no, well, as someone who's busy but has observing resources they can put to it, is there a way you can just email them to the microlensing community, or?
We have a spam list.
Okay.
So if you want to, join, let us know. Łukasz will add you.
Thank you.
So as far as I see the right curves of the Gaia on one of the events of the alerted by the Ogo in a Bausch, looks like it's not that bad in a crowded field. So is there any special effort was made?
So it was quite shocking for me because Gaia before like I don't know June was doing very bad in Bulge, and after June there was like a scan through galactic plane, and I found a lot of microlensing events both in Ogle and in Gaia, and that is because Gaia has gathered a lot of baseline, and that's how the alerting was improved. I hope I answered your question.
What's your delay time for getting Spitzer observations? What's your protocol?
So first we find good candidates, and then if they are bright enough, we make a spectrum, and then we send it for check the if they are when will they be observable for Spitzer. So it's kind of like.
When from the time that you tell Spitzer about it, how long till you get an observation picture?
Oh, I don't know. How long, Łukasz?
Well, these are long events, so we don't
Yeah.
rush.
Yeah.
Weeks.
Yeah, it is weeks.
6 weeks delay time between telling them and getting the observation?
Yeah, I think so, yeah.
Okay, let's thank her again. And to wrap up the morning session, we have Chris Rybicki to tell us about astrometric microlensing in the era of Gaia and W1st.
Thank you. Okay. Thanks. Hello, everyone. My name is Chris Rybicki, and I am a PhD student in Warsaw Astronomical Observatory, and want to tell you, obviously, about astrometric microlensing. It's well, near future and slightly farther future, which is Gaia and W1st, obviously. Let's just hope that W1st is not too far from here. So as much as we like microlensing events as they are, as the observational, from its observational part, we actually want to use them for something, right? So, so yesterday we had many beautiful talks about planetary microlensing in the using microlensing for planetary events, but today at least few talks will be about well, more violent objects, which are in general sterile remnants, but well, most interesting probably would be star mass black holes, but you can essentially think of many objects that are interesting and invisible, like mergers from gravitational wave events, or you can even imagine intermediate mass black holes flying through the galaxies, and essentially anything that is intrinsically invisible is potentially interesting for a microlenser science. You can actually detect, you can hope for measurement of mass of such objects. And yeah, so as for astrometric microlensing, I don't want to go into details because you probably know them already. But this is the formula, the most important formula for us, as Kasia already shown. So the parallax, to measure the mass, we need two components, essentially, parallax and theta e. And so Kasia already said that. But if we are looking for stellar remnants, we also probably want to have blending parameters as well. We want to have as little blending as possible, since well, our lenses are dark, obviously. And now, just on the lower part of this slide, just to remind you, I already shown that to you previously. We did some theoretical predictions about what Gaia can do with addition of precise ground-based follow-up, well, precise ground-based data, and well, the results weren't that optimistic as for this case. But yeah, we still hope that there will be few events that can have masses measured at the end of the Gaia mission from this previous work. But as we are getting closer to the actual data, we want to think about finding good candidates for measurement of potential astrometric signals, and this would be from all of the service, essentially. Well, from OGLE, also followed events alerted by Gaia. So the problem with we haven't dealt with yet with Gaia is that, as we heard today, that everything that is fainter than 13 magnitude does not have both directions downloaded to Earth. We only have one direction, a long scan direction. When Gaia is scanning the sky, the stars are passing through these astrometric fields, and as I said, only the brightest star will have two-dimensional astrometry. So going back to candidates, we picked few for our, well, let's say, tests. What can be achieved, very preliminary ones, very naive. But well, when collecting this sample or these few events, we obviously had to concentrate on brightness of the events. This was the main cut, because the problem with Gaia is that the microlenses usually are rather faint, and the precision of Gaia falls dramatically with the magnitude. So we had to pick as bright events as possible, of course, as long as possible, to have higher probability to obtain to mass of the lens to be high, and with, as I said before, with as low blending as possible. So for such events, we did some modeling with simple models of single lens with parallax, and to create potential astrometric signal, obviously we had to do some assumptions. So so do not get too attached to this mass. For example, you can have whatever you like, essentially. But on this right plot, you have on the upper panel, you have astrometric deviation, astrometric shift, that potential astrometric shift you can have from this event with this configuration. And then on the lower panel, there are, if you have only one-dimensional measurement, you have to somehow convolve direction of the Gaia scan direction, of the Gaia along scan direction, and direction in which the deviation appears. So on this lower plot, you would have, well, this is what we can expect from these very naive assumptions. For example, in this case, for such event with such brightness, which probably would be G around 16, this would be probably buried in the noise science. The Gaia accuracy would be probably 200 or 300 of microarc seconds for such regime. So yeah, this is pretty similar. I don't want to go into many details about this. This event shown already by Kasia and Yossi yesterday, Gaia 18 BMT. Here we have more hopes to detect something, since the configuration of the shift and Gaia epochs are rather promising. But still, we can't say anything without the data. We also have, as has been said, follow-up from Spitzer. And this is the favorite, obviously, Gaia 16 AYE from the naive convolution of the scan directions and direction of the shift. You may think that that the shift will be of the order of milliarc second, but still it's nothing certain. So okay, that's a very little of time. So going to the W first now, because that's why we're here probably. We did some tests for W first as well, and did pretty similar thing to what we did in our previous research. We picked an example of event that we expect to be a black hole, for example, and example of a more normal, more standard microlensing event. Here it would be, well, half solar mass dwarf. Not very standard because, as you can see, it's quite close, but we want to check how W first can be helpful in detecting, in measuring mass of in such events. This also was mentioned by Samson yesterday, the cadence of the W first. Just to remind you, what is spectacular here is the 15-minute cadence, which improves accuracy dramatically, and well, the cadence is also somehow peculiar because there are 3 seasons at the beginning of the mission and 3 seasons at the end of the mission, which also obviously have big implications on detection efficiency of microlensing in general. So with W first itself provides photometry and astrometry, so we didn't need to look for any ground-based additional photometric data, either ground-based or from somewhere else. So what we just did, we picked these 2 events, we added some proper motion and check how they would look like with predicted accuracy of W first, which was simulated by Sebastian, I think. And yeah, and this very simple pilot looks very promising because while it's obvious that for black hole it's the data looks very good, even for well, less spectacular, less extreme events, you can see some signals here. So we fitted our models, both photometry and astrometry simultaneously, and we got to mass measurements for black hole and for this dwarf with accuracy respectively few percent and around 20%, I would say. So it looks promising, and on this slide, the last comparison between W first and Gaia, as you can see, it's much better. You can really expect to detect something with W first. But it's not like Gaia fails somewhere, right? It wasn't designed for that. It does very well in what it was designed for, which is, well, averaged astrometric parameters, proper motions, parallaxes, but not per epoch data. And two main reasons for that are cadence, as I mentioned, and this dramatic drop of precision with brightness. Because if every microlensing event was 12 magnitude, then fine, and Gaia is enough. But as you know, it's not the case. So these are thoughts to take away with you, and I stop here.
I would suggest that you also consider the possibility of getting W-first observations in the non-planet search seasons. This is something you could propose to do, and if that could increase your sensitivity, give you many more black hole discoveries, then that would be a very strong GEO proposal.
Okay, thank you.
Locations in the galaxy where you're sensitive to black holes?
Right.
Where can the black holes be living?
Well, I don't know. We are going from the other side, rather, where our microlenses. Then we are hope to get a black hole, because.
Right, but for the stars that are the black holes are the lenses, right?
Yes.
Right. So where, like, can you look in the galactic center, for example, or is that too far away and you don't have stars behind there to use there?
Yeah, well, yeah, this is the reason. We want to look at the galactic center because...
So you'll actually constrain the galactic... Okay, that's awesome. Sorry, I'm not a microlensing.
Yeah, sure, but I'm not sure if I understood the question. We want to look everywhere where microlensing appears, and then we hope to somehow measure the mass of the lens during the event. So it's not like we are looking for a black hole, and then we hope that this object that we hope is a black hole will somehow microlens something in the background.
So, yeah, I mean, to answer her question, I think Ruth's question is, for the microlensing, for the W-first microlensing survey, it's all towards the galactic bulge. And it could be and about 60% of the lenses are expected to be in the bulge, 40% in the disk. But of course, we have no idea what the black hole distribution is, so who knows what that could be. For the Gaia black hole detections, which she said are marginal or harder, those are obviously could be all over the sky. So it could be anywhere.
So if there's a large population of black holes that we don't know about right at the galactic center, would you expect to see them?
Yes.
Okay, awesome.
Wait, Hal, wouldn't they be too faint? There's a ton of extinction there, and he's using Gaia photometry.
No, we're using W-first photometry. Oh, at the very galactic center? You mean the central? Oh,
she means black holes are in the galaxy.
So you maybe I'll leave that to Jessica. She might discuss that during her talk. But it's possible we can modify the microlensing survey to do occasional observations at the galactic center exactly in order to look for things like this.
Yeah, thank you.
Totally a separate question. This is completely out of left field, but people may have heard that there might be a planet 9 out there. People may or may not believe that this evidence for this exists.
You mean Pluton?
No, don't mean Pluto. Pluto is not a planet, and don't get me started, because I will defeat you. But no, this paper by Constantine and Mike, this idea that they've been pushing. I wrote a paper with Josh Bloom years ago suggesting that if there was a massive object in the outer solar system, it would produce an astrometric shift of a bunch of stars as it moves back and forth due to not its own proper motion, but due to our relative motion. And therefore, you might see a bunch of correlated astrometric deviations due to an object that you might not be able to otherwise find. And since they have a rough idea of where they expect this thing to be, I think it's marginal whether or not you could detect it depending on whether or not it's near a region where there's a lot of scans or not. But has anyone looked into this?
Well, I haven't. So, but what was the expected order of magnitude of the shift?
Well, so as I remember, it
But they know where to look, or
Well, so they have located into a rough, very large
okay,
patch of sky, but not 4 pi.
yeah, maybe it's
So well, you'd look for correlated deviations of stars on a particular location in the sky to try to.
okay. Yeah, maybe it's worth checking.
Okay, let's thank all the speakers again.
Thank you.